get ready for the Wright Brothers lecture. So if you would take your seats, we'll start in a couple of minutes. Welcome to the 2023 AIAA Wright Brothers Lecture in Aeronautics. We're happy that you could join us this afternoon. I'm Fay Collier, and I'm a member of the AIAA Honors and Awards Committee and chair of the Wright Brothers Lecture and Aeronautics Subcommittee. A little bit of history. The Wright Brothers Lectureship commemorates the first powered flights made by Orville and Wilbur Wright at Kitty Hawk in 1903. It recognizes the success of their approach to problem solving, beginning with the study of the literature, including the innovative thinking, constructive debate, systematic testing, and teamwork. This lecture has been presented since 1937, spotlighting distinguished leaders in aeronautics, including Hugh Dryden, Edmund Allen, Theodore von Karman, Glenn Martin, Stark Draper, more recently Bob Liebeck, Gene Covert, John Swihart. So I now invite our 2023 lecturer, Larry Young, to the podium. As Larry comes up to the stage to deliver the lecture this evening, I'd just like to say a few words about Larry's background. Larry, come on up. Larry is an aerospace engineer at NASA Ames Research Center in Moffett Field, California. He's conducted rotorcraft and vertical flight research in the Ames Aeromechanics office for over 40 years. He performs research on advanced aerial vehicle and aerospace systems conceptual design. Among his current and past projects are studies into the fundamental vortical flow physics, planetary aerial vehicles, rotary wing vehicles for disaster relief and emergency response missions. Larry was an early researcher into the Mars rotorcraft and other vertical takeoff vehicles for planetary exploration. He received his Bachelor of Science and his Master of Science degrees in mechanical engineering from Washington State University. And he's a technical fellow of the Vertical Flight Society and an associate fellow of the AIAA. So now, if you would, please help me welcome Larry, who will deliver the 2023 AIAA Wright Brothers Lecture on Aeronautics entitled NASA Aeronautics Contributions to the Ingenuity Mars Helicopter. Have fun, Larry.
Thank you very much, everybody. Okay, good. Getting arranged. First of all, I'd like to thank the AIAA for this great honor to be a representative of the Ingenuity Mars Helicopter Development Team. And that's really what I am. I'm just merely a representative. The development team represents Jet Propulsion Laboratory, NASA Ames, NASA Langley, AeroVironment, Qualcomm, SolAero, and Lockheed Martin, all of which contributed in major ways to the realization of the Ingenuity vehicle. And additionally, I want to highlight here, I'm going to be talking about, when we talk about NASA aeronautics contributions, I'm going to be talking about aeronautics with a little a and a big A. And particularly with a little a, I'm going to be talking about the fundamental aeromechanics, aerodynamics, flight control, all that good technical disciplines that go into successful aircraft. But I'm also going to be talking about the big A because really the personnel who contributed from NASA Ames and NASA Langley were members of the Aeronautics Research Mission Directorate Revolutionary Vertical Lift Technology Project. And that was the one that helped enable our participation in the project. So again, highlighting this theme of it was a team effort. These are just a limited selection, a limited list of the people who contributed to the development of Ingenuity. And at NASA JPL in particular, I'd like to highlight the project manager, Mimi Ong, the chief engineer, Bob Balaram, and the chief pilot, flight dynamics control lead, Hobart Grip. And as you can see here, there's quite a few people here, but ultimately at the end of the day, when Ingenuity was successfully developed, there were dozens and dozens of individuals that participated in the project. So if you, by chance, you wandered in here and you don't know what Ingenuity is, this is a picture just to kind of reinforce what it looks like. And it's a small helicopter that's been flying on Mars for over 2 years now. Specifically, its mass is about 1.8 kilograms. It's a two-bladed, two-rotor, coaxial rotor system where the rotors rotate opposite to each other. It's 1.2 meters in diameter. And a very important characteristic is in terms of propulsion, it's solar electric propulsion with battery charging. So it'll actually sit on the ground, have a solar array that's mass mounted to the top above the rotors. That electricity would then charge the batteries and allow a flight approximately when the initial technology demonstration phase occurred. It took about 1 or 2 sols or 1 or 2 days in which to charge the batteries for another flight. Because this is the Wright Brothers lecture, and because people in the past have made comparisons between Ingenuity and the Wright Brothers experience, I thought I'd try giving my viewpoint on this as well. Now, I want to be careful here to emphasize the fact that I'm not an aviation historian. I'm not even an amateur aviation historian. So keep that in mind as I'm talking through this particular aspect. But I think there are some very fundamental things there's parallels between the Wright Brothers experience and Ingenuity. And first of all, which is the first bullet here, which is there were decades of trial and disbelief before each flight was successfully realized. And I'm going to talk about that a little bit further as we go through the slides. I'm also going to talk about the importance of innovation and prototyping. That was part of the citation call for the Wright Brothers Award, but it's also nonetheless true not only for their experience, but for Ingenuity. The importance of experimentation, and then some comparisons between the two different first flights. Now, this is just the first section of the presentation. As we go through the presentation, I'll be talking very specifically about some of the aerodynamic challenges and support that was provided in order to help realize Ingenuity. So, with regards to trials, decades of trials or more of trial and disbelief of the Wright brothers, humankind dreamed of human flight for hundreds of years. And the air screw of Leonardo da Vinci was just one particular noteworthy example of that. And even up until the time of the Wright brothers, there was still active ongoing research going by the parts of Samuel Langley, Otto Lilienthal, and others to help make possible the realization of flight. The Wright brothers did it. Unfortunately, those other individuals didn't. But nonetheless, the lessons learned, the experience, and the insights that those pioneers developed helped enable the Wright brothers to succeed. And here's the thing. Even the Wright brothers, up until their successful flight, had their doubts. And that's, I think, an important point, because when you attempt to do something really momentous, if you don't have doubts, you're not being adequately serious about the problem. And the Wright brothers clearly were serious. And even after the Wright brothers succeeded, it took a long time for that to sink into the public consciousness. And they had to not only continue to promote the flying and within their organization, but it still took a long time to succeed. Ingenuity. Even after 5 decades of research and advocacy since the Viking landers clearly established how thin and how cold and how primarily dominated by carbon dioxide Mars' atmosphere was, there was very few people who believed that aerial exploration of Mars was really practical, okay? Maybe theoretically possible, but practical, there was a considerable amount of doubts. And further, other than just a few dedicated pioneers, nobody at all really saw that from the scientific and technical community saw that, vertical lift aerial vehicles were possible to fly on Mars. Despite that, there was a body of research over the past 25 years looking into Mars rotorcraft within NASA, specifically within NASA Ames in particular. And the point is, despite that, and despite the successes of the developing Ingenuity, it really was only till the time of the first flight of Ingenuity that there became this broad acceptance of the idea that flight was possible on Mars. I'm now going to talk about the importance of innovation and prototyping, the common experiences between the Wright brothers and Ingenuity. You see on the right here some famous pictures from the Library of Congress, looking at both the aerodynamic wing design, the vehicle design, as well as the propulsion design, the internal combustion engine being shown on the bottom. Innovation and prototyping were critical to the Wright brothers' success as well as Ingenuity. In both cases, there had to be advances in aerodynamics, flight control, and propulsion in order to succeed. Specifically, there was even a further challenge for Ingenuity in that not only was compressible low Reynolds number aerodynamics for airfoils and rotors not really fully captured at that point, there had to be advances in using micro-mechanical actuators and electronics. We had to rely a lot on COTS type of electronics that previously, if this wasn't a tech demonstrator, would not have been adopted into an aircraft. Solar electric propulsion, I already talked about how that was a significant advance. If we didn't have solar electric propulsion, the flights of Ingenuity would have been limited. Even though it may have had vertical takeoff and landing capability, it wouldn't have been able to string together the succession of flights that it has done to date. And then the last two bullets really are representing the fact this is a spacecraft as much as it's an aircraft, and so therefore spacecraft design considerations have to be fed into it. And that includes how do you take a fairly large, volumetrically large vehicle and stow it in a manner that can fold underneath, in this particular case, underneath a rover. And additionally upon which it has to survive the environmental conditions, not only on Mars, but it has to survive the environmental conditions during launch, in space transit, and then entries, descent, and landing as well. Importance of experimentation. You see in the upper right, one early version, one of the Wright brothers' wind tunnels to get a better understanding of wing section lift. And on the bottom, you see what's called a wind wall. It's basically, this is inside the JPL 25-foot space simulator where they crafted through a bank of hundreds of ducted fans an open jet wind tunnel to study both the performance and the flight dynamics characteristics of not only the flight model, but engineering development models and a prototype. And more will be discussed as we go through it. And then finally, first flight, Wright brothers, 120 feet in 12 seconds. Ingenuity, a hover about approximately 10 feet and about 39 seconds as well. So now I'm going to transition and talk about kind of the bigger picture here. I talked about 5 decades of people after the Vikings trying to develop aerial vehicles, and some out here might wonder why a Mars helicopter versus a Mars airplane versus other type of things. And in fact, the bulk of Mars exploration proposals using the aircraft were Mars airplanes. But other configurations were also studied as well. There were ornithopters, there were balloons, airships, gas hoppers, a variety of different concepts besides just Mars rotorcraft. In turn, as I previously noted, Mars rotorcraft has been studied since the mid to late 1990s, and it really seriously began being studied in 1997 at NASA Ames with I and a number of colleagues as well. And the thing that we're going to do here, and we'll touch upon at the very end of the presentation, is this also, the success of Ingenuity, in my opinion, is also enabling the success of not only future Mars aerial exploration, but other planetary bodies as well. And at the same time that we were studying Mars rotorcraft, we were also looking at other vertical lift vehicles for other planetary bodies. The first planetary aerial vehicle was 2 balloons that were released on the Soviet Vega 1 and Vega 2 missions, and they were released at high altitude, approximately 54 kilometers, under relatively benign type of environmental conditions. The density was approximately that of Earth, the temperature was also approximately of Earth. Talked about, maybe many people in here were participated either on student intern design projects that looked into Mars airplanes, or actually wrote technical papers on them, or in fact even made proposals to study the vehicle. And this is kind of a survey, and so I'm recognizing here kind of all that historical context with these things. These are a limited number of publications. It's not comprehensive. There are literally hundreds of Mars airplane type of citations out there, but it gives a feel for the range and the vehicle mass that were proposed previously. Arguably, the most influential Mars airplane concept of all was the Dryden Mini Sniffer that also advanced not only potential research into Mars aerial exploration, but also high altitude, long endurance type of surveys as well. The reason why the folks are in the hazmat suit is that they actually developed a reciprocating engine that used hydrazine, a very toxic monopropellant, to drive it for a while. Unfortunately, this only got to roughly about 18,000 feet, but it shows the advancement of the technology at the time. More Mars airplanes being proposed. The most noteworthy one is the one at the bottom right corner, which is the Ares platform. That actually saw a fair amount of investment on the part of the ARMD at the time, and actually was ultimately almost selected for a Mars mission. As I said, Mars rotorcraft really began to kick in about 1997 within NASA, but even back in those days, as you can see from this graphic, that circa early 2000s, we were already looking at coaxial helicopters. We were already looking at integrating them with rovers, doing missions with rovers. And so that kind of mission continuity, that overarching ConOps, is still continued to this day with Ingenuity. Early work focused on critical technologies. We're a research organization within NASA Ames and NASA Langley. And so that's really where we started beginning looking at everything from conducting the first documented, published hover test in Mars-like conditions, which you see in the upper left graphic. On the right-hand side graphics, early computational work for that Mars rotor operating conditions. And then finally on the bottom left, we actually did Mars analog testing at remote sites that were evocative of Mars with small surrogate vehicles. Then, about 9 years ago, JPL proposed in 2014 what eventually would become the Ingenuity helicopter. And almost from that very beginning, JPL did work with NASA Ames and Langley on that effort. And as I noted, this was really sponsored on the NASA Ames and Langley side by the Revolutionary Vertical Lift Technology Project within ARMD. And this is just a graphic of kind of the kickoff meeting here that was located at NASA Ames. Again, emphasizing you have to consider this particular mission. Not all Mars rotorcraft and not all Mars aerial vehicles work in coordination with rovers or landers. They can, and obviously Ingenuity does, but they can also be standalone platforms. But from the very beginning, Ingenuity was conceived as working closely with and deployed from the rover. One of the interesting factoids was originally Ingenuity was to be deployed between some of the wheels on the rover by some deployment mechanism. It was only that the development was fairly along that it became possible to deploy it from the underneath of the belly of the rover. So the one other point about this is that Perseverance is actually the communication link between Ingenuity and Earth and back. And so that's why there's kind of this back and forth between not getting too close, but not getting too far so that telecom can still continue to occur. So now I'm going to transition, as I promised, to get into some of the more details about the aeronautics contributions with regards to Ingenuity. And I'm first going to talk mostly about the aero performance issues, or basically the aeromechanics, the aerodynamics, the vehicle design, those aspects underlying it. So we participated, NASA Ames, NASA Langley on rotor design and peer review support. There was limited to almost no airfoil characteristics for the airfoils that were used on the Ingenuity rotors. These were developed by AeroVironment, but there was a limited amount of data, particularly a limited amount of data for the operating conditions on Mars. And so we conducted a considerable amount of two-dimensional CFD in order to get the airfoil characteristics that would then use in standard rotorcraft analysis tools such as CAMRAD. And that's the comprehensive rotorcraft analysis performance modeling that I referred to. We also did high fidelity CFD, and that again was starting to look into the solar array panel became larger and larger so that we could maximize the amount of electricity generation capability, and so there were concerns about whether that was going to impede the aerodynamic performance as we went into forward flight. We did the first ever surrogate Mars rotor testing, not at the JPL 25-foot space simulator, but NASA Ames has a large low-pressure chamber as well, and uniquely, it also has a moderately sized wind tunnel that was originally developed for Aeolian dust studies for Mars, but it actually was capable of being tested at like a 40-inch diameter stack rotor system as well. And then we also performed small-scale dust kick-up studies as well. And yes, we do kick up some dust. CFD results, this is just a picture of the Ingenuity airfoils, and additionally upon which shows that, just some of the vertical structure that are being kicked up here. We then took those airfoil characteristics, we imported into the comprehensive rotorcraft analysis tool. It's a standard tool. We did various different performance predictions. And we also, in turn, used another well-known NASA tool, Overflow, to look at the high-fidelity stuff, as well as the airfoil characteristics. This is just a sample of the hover results, which are in the circles, and the black and dashed lines are, in fact, the predicted tool output. And as you can see, there's reasonably good matching of performance. Figure of merit, for those who don't know, is the ideal rotor power divided by the actual rotor power. So you want to get that as high as possible. Again, Overflow, higher fidelity computations. See how this goes. This video may not work, but we did run both hover and forward flight. This was from NASA Langley and participation. No, it doesn't look like it's going to go. Oh, there he goes. Wonderful. Just, showing maps of isosurfaces of Q criterion and velocity magnitude here in hover. Did performance predictions again. It was a big accomplishment to show that standard tools, when you did things right, were able to match Mars-like conditions for rotor operation. Here you show the solid line is Overflow, and again, those circles are the experimental data. So relatively good matching there. However, forward flight predictions, slightly tilted forward, the wind coming from the left to the right. You see the big solar array panel on top of it on the upper left corner there in the orthographic viewpoint, isometric viewpoint. Mentioned the fact that we did surrogate rotor testing here using a stack rotor system inside the wind tunnel, which is at the bottom graphic picture there. Illustrative example of getting the experimental data, but comparing it to a mid-fidelity CFD tool that we use to help look at things like facility interference effects and recirculation effects when we operated rotors, both in hover and forward flight, in chambers such as the 25-foot space simulator. Dust kick-up studies here. The gray isosurfaces is an early prediction of some of the dust kick-up. Yes, Ingenuity will kick up some dust. We did small-scale model testing as well in parallel. There you go. You can see lightly some dust being kicked up. We'll come back to that as we get a little bit further here on the discussion. We did a considerable amount of facility development efforts, just like the Wright brothers. They had to build their own wind tunnel, and we had to, verify that Ingenuity we could get good performance numbers out of a relatively large chamber, but still, as we found out, still a significant amount of flow recirculation in that chamber. And we also had to simulate, wind gusts and perturbations, and we also had to get some sense of its operation in forward flight. And the way how we did that is, for the first part, looking at gusts, we had a swing arm. We actually had an arm that Ingenuity was mounted to that had a gimbal, and we moved it back and forth to simulate, gusts and all that, and looked at the response of the flight control system to those gusts through system identification. We looked at a variety of techniques in which we could do forward flight testing. Unfortunately, the Ames wind tunnel was too small to do Ingenuity type of testing, so we had to come up with alternatives. These are some of the alternatives we looked at. We finally settled on the blue-fonded JPL Caltech fan array, AKA wind wall as well, and we'll talk a little bit further about that. Continuing on that, we did a lot of computational work, looking at, again, how do you effectively test in a big, but still not big enough chamber to go ahead and look at, avoid negative adverse implications of the data by flow recirculation. And one of the ways we did it is we did some early testing with, a surrogate rotor system hovering in the Space 25-foot space simulator. At the time, at 1 atmosphere conditions, but if you look at the normalization of the parameters, if you match the CT, even though you're operating in 1 atmosphere, you're matching the velocities. And what we primarily were trying to capture was that swirling pattern that you see in the corners of the circular chamber that reflect the weight coming down, impinging on the floor, spreading out, forming supervortices, and then going up to the top of the chamber and getting that quantified. We also did comparable amount of mid-fidelity too, so looking at, if you look at the upper right chamber, that's the exterior view of the 25-foot space simulator. The graphics below represent, this mid-fidelity CFD predictions of the open jet flow behavior interacting with the rotors in forward flight of Ingenuity, as well as interacting with the chamber side walls and floors. And so a lot of work went into that to come up with the best design of positioning the fan array relative to the helicopter, the orientation of the helicopter, having it thrusting down and the weight going up, and other type of parameters in order to come up with the best configuration possible to have the most representative open jet forward flight testing that we could achieve. Another major element that was supported by the aeronautics side of NASA for the Ingenuity Mars helicopter was system identification analysis and flight control development. And particularly every single vehicle, either was, the prototype, the EDM, the flight model, were all put on the swing arm, and in fact, ultimately, except for the prototype, was put in the wind wall to help have the vehicle on a gimbal, being perturbed, putting in cyclic inputs, as well as the flow perturbations, to ultimately go through the system identification process to come up with the best flight control modeling that we could do in advance. And that literally was completed just prior to shipping everything off to the launch for the vehicle. This is the vehicle. This was the very first prototype, May 2016. This is the first time that the vehicle flew. Just some of the characteristics: it had gravity offload to take into account the difference between Earth gravity and Mars gravity, and it flew in the chamber. Okay. So more of the system identification. Again, this is an example of the coaxial helicopter on that swing arm. That's the horizontal element that goes into the page there. Let's see if this works. There you go. So now you're spinning up the rotors, and pretty soon the swing arm is going to be moving back and forth. And this is simulating, again, wind gusts of various different magnitudes and velocities. You see it moving back and forth, that chamber, walls, and the backdrop, moving back and forth. And then there'll be another video here that'll show the orientation of the vehicle being turned upside down, being on a gimbal, and now they're putting in cyclic control inputs to cause the vehicle to rock within the gimbal and get the derivatives out of that. The very first flight of a representative Ingenuity configuration, its prototype, occurred in May 2016. You're going to see the video here of that very first takeoff. Again, you can see the chamber surrounding it. The vehicle's on the floor. It has a gravity offload tether. It has electrical harness. That's part of how to compensate for the gravity difference between Earth and Mars. So all the batteries were off on the ground, and it just had a tether putting the electrical feed up there. Took off. Two things. Obviously, it was able to take off, provided the amount of thrust that we hoped it would provide. But the other important element of it was, though this was the first flight and is a little rocky, it still demonstrated the fact that despite the flow recirculation in the chamber, it was able to have adequate control in the chamber. And that was a big deal. All that information from the SysID effort went into the simulation model. The simulation model then was used not only for the development of the vehicle and its flight control laws, but it was further continued to be used all throughout the operational phase of the vehicle. Now I'm going to go transition from the development phase to the operational phase. The operational phase, I'll have to admit, is mostly being led by JPL. NASA Ames and NASA Langley are not really contributing at this point significantly. We're just basically cheering them on here. But nonetheless, I'm going to go ahead and give you guys a sense of some of the accomplishments of Ingenuity here. So, launched in 2020, crossed fingers, hope the rocket didn't blow up. It didn't, yay. Landed in the Jezero crater on February 18th in 2021. First flight was on April 19th, 2021 from Wright Brothers Field, which was intentionally named by the JPL operational staff. And it has flown 51 flights to date, and but the 50th was on April 13th, 2023. And the important point about it was that Ingenuity was authorized to be a technology demonstrator. It was only supposed to do 5 flights over 30 sols being 30 Mars days. It's been flying nearly 2 years. Well, actually, it has flown over 20 years, 2 years. It survived, even though it was never designed to do it, to survive the Martian winter and still be operational. And the aspects about the Martian winter is that it's significantly colder than originally Ingenuity was designed to, and also the fact that there's a significant amount of atmospheric dust buildup. And the dust buildup reduces the output of the solar rays, and therefore further increases the chances that Ingenuity would not wake up when finally it warmed up during the day and began to try recharging. But it survived that. And you can see in the graphic here just some of the meandering flight path, if you will, of Ingenuity in the purple line there. And right now it's poised on top of this big ancient river delta on Mars, where basically water theoretically tumbled down the crater rim of Jezero crater and formed not only this riverbed, but also build up a delta. And it's now working as a partner with Perseverance rather than just as a technology demonstrator. When the technology demonstration phase ended, it then went into this operational phase where it became a partner for Perseverance. It became the true aerial scout for Perseverance that one possibly could hope it to be. I'm now going to we talked briefly about doing small-scale testing with dust kick-up. I'm now going to go ahead and show a video of Flight 47 that clearly demonstrates there is dust kick-up when the vehicle takes off. If you look closely, you can start seeing, a super vortex spreading out from the vehicle. And why is that important? Well, that's important because that's one of the things that might result in Ingenuity one day not being able to fly anymore. Because there is dust buildup, progressive dust buildup on its solar arrays, partly because of the atmospheric dust from the winter and partly because of these dust kick up when it takes off. And so one day it may come to pass that it will not be able to adequately generate enough electricity to fly again. So some of the major accomplishments of Ingenuity demonstrations accomplishment was the first deployment of a semi-independent robotic platform from a rotor. Forget about an aerial vehicle. It's the first time that you basically kicked something off a rover, had it do it something independent of the rotor to assist the rover's mission. And of course, yes, it was the first powered flight on another planet. Additionally, vitally important, it sustained multiple flights. It demonstrated mission persistence. We were no longer talking like we were in the days of Mars airplane, the early Mars airplane talks, about a single flight that might last a few minutes. We were now having flights that could be strung together over the course of months. And so, as I also noted, we transitioned from a tech demo phase to an operational phase where we're actually now supporting Perseverance. Briefly talk about the future Mars rotorcraft. There is ongoing. There's a growth version of Ingenuity that's being developed. There's going to be 2 helicopters called the sample recovery helicopters. They're now going to be able to carry a payload of approximately 500 grams, whereas Ingenuity was not capable of carrying any payload other than just the onboard cameras that were necessary for navigation. And these will actually be a backup option that if Perseverance is not able to deposit these sample tubes that they've been collecting samples from the surface of the planet and then installing them inside an ascent vehicle for the sample return mission, theoretically, these sample recovery helicopters will act as a backup and do that for Ingenuity. And not only will it be able to have greater payload capability because of being a growth variant, it's going to have small little wheels on it so that it can move the last few meters on its own on the ground so they can get close to the tubes without landing next to the tubes. And it'll also have a small robotic gripper or arm to pick up the tubes and then take them and put them into position for the ascent vehicle pickup. There's also another potential vehicle that's a large hexacopter. Basically, each of those individual rotors are the same diameter as Ingenuity, but instead of 2-bladed rotors, they're 4-bladed rotors, and there's 6 of them. And so we go from, a 0 payload capacity for Ingenuity, so now we're talking about, for a vehicle that's approximately 30 to 60 kilograms, maybe 3 to 5 kilograms of payload, which is important for the scientists to now seriously consider Ingenuity, a Mars helicopter, not just being a aerial scout, but in fact a platform, a utility platform, a role that's really well used for the helicopter community to carry scientific instruments to make measurements on the planet. And obviously there's other ideas that are also being thrown out. Again, Ingenuity was an inspiration. It did more than just demonstrate the flight on Mars. It also demonstrated the fundamental aspect that you have a vehicle that can do vertical takeoff and landing, and through electric propulsion, it can sustain a large number of flights, and therefore have a sustained mission. So in that regards, it has possibilities not only for Mars, but for Titan and for Venus, and maybe changing the attitude of people doing field science in remote areas autonomously with small Earth UAV, rotary wing UAVs as well. Right now, the next Mars rotorcraft mission is under development, and that's the Titan Dragonfly. It's a nuclear battery-powered vehicle that's the size of a small automobile. It's an octocopter, as you can see in this configuration here. That's been authorized. It's going to be launched in 2028. It's going to take a large number of years to get to Titan, but that's the next big thing. So go Dragonfly. So I'm going to wrap this up in here. I'm going to make some acknowledgments. I want to basically make a thank you to all the early pioneers of planetary aerial vehicles and Mars rotorcraft. And there are probably people here that would consider themselves to be part of that community. And I say thank you to you. And I thank you to your students that you helped inspire in that regards. I want to say a huge thank you to the dozens of individuals and organizations and companies that participated in Ingenuity development and operational teams. I hope I've done them some justice in terms of communicating the magnitude of the work, in terms of how, challenging it was and how all proud we feel that we helped make this happen. And then finally, very importantly, and this reflects to the pictures down below, we talk about STEM within NASA. I have to believe that Ingenuity, one of its great legacies, besides inspiring the development of other planetary aerial vehicles, it's going to inspire a new generation of planetary aerial vehicle designers and Martian aviators. And with that, one last Wright brother connection. Underneath the solar array panel that's above the top rotor of Ingenuity, they're wrapped within orange tape, is a piece of the 1901 glider fabric. And that's underneath the vehicle right there. Okay, so a little bit of the Wright brothers is flying on Mars today. With that, thank you very much for your attention. I appreciate it.
Larry, I'm going to give you a certificate and a medal at this point. Bear with me for just a minute because I want to make sure that the audience knows that there's going to be a little time for Q&A. And we have a couple of ways that you can do that, the standard submittal through the website. And then we'll maybe even take questions from the audience. But in the meantime, while you're thinking of your questions, Larry, I'd like to congratulate you on a wonderful lecture. Learned a lot. And I've got a couple of things for you back here. Let me start with the medal. Thank you, Larry.
Thank you.
And then we have this certificate for the 2023. I think we probably want to face our cameraman here.
Okay.
Wright Brothers Lecture in Aeronautics presented to Larry Young for the NASA Aeronautics contributions to the Ingenuity Mars helicopter. Thank you, Larry.
Thank you very much.
Let's get a picture. Well done. It's a great story.
Thank you.
So I'm gonna start with a couple of questions. As a technology developer, you made that seem so routine, complete success. It looked like just an engineering project. There must have been a couple of oh crap moments.
Yeah.
Would you like to amplify on some of those or not?
No, I mean,
Completely up to you.
I would be happy to. So, you know, I think the first major challenge that people have to appreciate is that you really have all these people from different backgrounds and different perspectives that you have to come together as a team to achieve things. And so, you know, if it was just solely vehicle designers and aerodynamicists and all that, and we were just developing an aircraft, no problem. But you have to reach out to planetary scientists, you have to reach out to spacecraft technologists, and you have to reach out to mission architects, and to be quite frank, you have to reach out to senior management within NASA to make this a realization. So that's the first challenge I think that we had to deal with, was just to come together as a team and as a community in terms of dealing with that. The other element of it is, yes, through the course of things, there's always weight growth that occurs. We had a big increase. Originally, Ingenuity was supposed to be hovering around about 1.2 kilograms. It ultimately grew to 1.8 kilograms before things finally came under control. And, you know, I briefly mentioned how we intended that the Ingenuity would basically be kind of nested in between a couple of the wheels of the rover. That basically got a big pushback on the part of the rover people and the mission architects that were backing that up. And we never fully appreciated the fact that there was an opportunity to ultimately do the more tractable problem, which is to have it suspended underneath the belly of the rotorcraft, of the rover under a protected thing. When we were doing the initial year and a half plus of work on that, we never envisioned that would happen. But once that happened, things started to come together. But nonetheless, that's kind of an understated element of here. Again, for this community, thinking about aircraft, really that deployment sequence is really critical, and Lockheed Martin was responsible for that, and that was an important element too. So yeah, there was a lot of moments where we kept on thinking, well, is this the end or not? And we, through the guidance of the project manager, Mimi Ong, who did a fantastic job, both in team building and team coordination, she did a fantastic job getting us through those hurdles as well.
Thank you, Larry. Do you have time to answer a few questions? We've got some coming in online.
I'm happy to answer questions.
Okay. First question. What were the key design requirements that drove the design towards a helicopter versus a fixed-wing airplane?
There's several elements, but with the ingenuity, I think it really came down to it always was being proposed to work in coordination with the rover. And it was always defined, if you will, in terms of its overarching mission con ops, that somehow it would be kind of a passenger, if you will, on the rover before it was finally deployed. And once you go down that path, unless you talk about trying to do some sort of rocket assist launch or something like that from fixed axis rover, you're not going to make a Mars airplane work. And on top of that, if you did say that you somehow could successfully use a rocket-assisted launch from a rover, you would never have the rover people accept it because the risk level was way too high. When we started out with the early discussions in terms of con ops with the rover and the vehicle, they wanted to have a safe zone where you never get closer than about 100 meters. Now, I think they've relaxed that a little bit. But see, that put a tremendous pressure. We couldn't get close to the rover, but at the same time, the rover was essential to us in that it was the telecom relay between Earth and the helicopter. So it was quite a give and take on that.
Got another one for you. How has the reliability of Ingenuity, a fully autonomous system operating in human-free environments, been ensured? There's a second part to this, but I'll let you take that one first.
Yeah, that's why there was such a huge investment of energy in terms of doing this, the extensive, full-scale engineering development model and flight model system identification. That was the path that they saw as doing that basic experimentation with the actual vehicle, not a scaled model or anything else, getting that information, building it into a simulation tool that then they could compare to the results of the flights in the chamber and with the wind wall and get satisfactory results. That was all essential to that path of verifying that there was going to be acceptable flight control. Now, along the way, there were nuances that had been done. The aerodynamic damping of Mars as applied to rotors is pretty much negligible. And so that drove us to, instead of using flapping hinges on the helicopter rotors, we instead had to have a very, very, very stiff rotor system to accommodate that. So that was a cascading thing that happened in terms of the basic flow physics and then driving the design. And then I think that, some people may be aware of the fact that there was a couple of software hiccups, despite all the testing that they did. For example, there was a timing issue with one of the FPGAs that they were using on the vehicle that basically very early in the flights, the technology demonstrator flights, they weren't able to spin up the rotors because the mismatch was too great. They corrected that problem. It still potentially occasionally will happen, but they've reduced the chances of that significantly. And then another thing that happened was that there was a timestamp dropout on some of the nav camera images that were being brought by the vehicle that were used for visual navigation, partial visual navigation of the vehicle. And when they had that timestamp dropout, basically resulted in erroneous flight control inputs into the vehicle that caused it to rock back and forth nearly uncontrollably, but it survived that, and then they corrected that problem. But if I'm leading you to believe that it was just perfect A to B, smooth sailing, no surprises whatsoever, that is not the case, okay?
Yeah. It seems so easy. Here's the second part of that question,
Yeah.
if you'll indulge us, Larry. Thank you. Has Ingenuity ever experienced any instances of toppling over during its operational period? And are there contingency plans in place in case of such occurrences?
Yeah, let me see if I can address that question. They actually did a lot of, for lack of a better term, iron bird testing of that, where basically they would drop a simulation, a surrogate vehicle that had the inertia and mass of Ingenuity at various different rates and at different angles and at different terrain features, all on Earth, all at one atmosphere, but they looked very carefully at that. Obviously they did, basic mathematic calculations on that, but they also did that fairly extensive testing of it to verify that when it landed, that basically it would not topple over from that. They also looked at, the implications of the winds, local winds on the vehicle, asking whether or not that was a big thing. But even though the winds can get fairly high, somewhere between 10 to 15 meters per second on Mars in Jezero crater as predicted, if you take into account the thinness of Mars's atmosphere, the forces were fairly negligible on the vehicle. So really it comes down to if Ingenuity ever does topple, it's going to be probably as a result of something that there was some large unforeseen rock that was in the location in which it landed, and then when it dropped that final meter or so, there was, after that drop of the final meters is basically they just shut off the switch and it drops down. So if it hits a rock or something like that, it might theoretically topple, but they did look at a variety of those type of scenarios with the Iron Bird vehicle that they looked at, that they used.
Very good. Do you have time for one more question?
Sure.
Okay.
My time is all your guys'.
For the next generation of Mars helicopters, what are the important enablers in the simulation or in your simulation approaches? And then how ready is that tool chain with parametric models?
Yeah, so I probably didn't emphasize it as much as I could have, but it really, really was very personally gratifying to see that standard, well-known rotorcraft tools, if carefully used with the right aerodynamic coefficients for airfoils and getting everything modeled as it should be, we're capable of modeling key features of Ingenuity. Not to say that there aren't areas for further investigation, there always is, but the point is it was still nonetheless gratifying that you could take tools that were developed for conventional terrestrial rotorcraft, and if used properly with best practices, they could help you in the aid in the design of a Mars rotorcraft. So that was the first thing. The second thing about it is that what has happened is that, and it was on my slides, but I didn't mention it, is that some of this, again, the success of Ingenuity sparked the Space Technology Mission Directorate to fund some early career efforts, where now they have a task in which they're basically coming up with tools, a tool chain, if you will, to go ahead and optimize rotors and airfoils uniquely for the Mars atmospheric conditions, and would be capable of accounting for the shifting of the very low Reynolds numbers, tip Reynolds numbers of Ingenuity, which is sub 10,000 to more into the 100,000 range type of thing. And you have to have that flexibility doing it. And as you move into that area, there are going to be unique challenges for that as well. So, but nonetheless, there is an investment of effort where they're looking at trying to optimize rotors for future Mars missions, future Mars rotors, for a spectrum of sizes, for a spectrum of capabilities in terms of relatively low speeds like Ingenuity, which has so far been limited to approximately 6 meters per second, to something that's more representative of about 30 meters per second, which would be probably that Mars science helicopter, hexacopter that I talked about a little bit earlier.
I've got one last question to end on. It ties into the Wright brothers. Was there a breakthrough moment or idea that made ingenuity practically possible, similar to the Wright brothers' wing warping concept that allowed controlled flight?
I think that it was uniquely the biggest challenge. The reason why JPL came to us in the first place to talk about it is that they had a very small scale vehicle they attempted to test in the 25 space simulator, and they couldn't control the vehicle at all. It would hop up and show that it could theoretically generate the amount of lift that they wanted, but it was just uncontrollable. And part of the reason for it being uncontrollable is even though you think that, a chamber that's 25 foot in diameter and it's 80 foot tall would be large enough that you wouldn't have to worry about flow recirculation effects on the control of a small vehicle, but both through the combination of the magnitude of that flow recirculation and that extremely low aerodynamic damping that I referred to a little bit earlier, it made that small scale vehicle totally uncontrollable. And so a couple of the fallouts was that they all decided from the very beginning that they would work with full scale models, not small scale models. And then further on top of which, we had to really get a handle on this flow recirculation. I would put it even more than just the flow recirculation. We had to demonstrate that we had facilities that we could somehow rationalize, we could use to test vehicles such as Ingenuity. And that was the fundamental core thing there. So it's a little bit different. It wasn't, could we come up with, a way of controlling the wings? Is more of, how do we test this to prove that we can fly and that then ultimately we can convince people that we could fly it successfully when we got to Mars. And so it was a little bit of a different challenge.
Thank you. Round of applause for Larry. Thanks again. Well done.
Okay, thank you.
And that concludes the lecture this evening. So thanks very much for your attendance and your attention. And we'll close it right there. Thank you.